So before I talk about equivalence relations, actually a lot of what I'm talking about is going to be in the setting of groupoids. So I'm going to introduce the setting of groupoids and say a little bit about how it interacts with equivalence relations. And I'll probably end up saying a lot of the statements and results in terms of groupoids, but a lot of it can be restated in terms of equivalence relations if you're more familiar with that setting. All right, so there we go. So what's a groupoid? For my purposes, I'm going to be thinking of, where can I annotate here? Am I missing an annotate button? Okay, I'm not sure how to annotate right now, so I'll just explain it. Okay, so for my purposes, a groupoid, okay, is just going to be a collection of objects, which later on in the talk is oftentimes going to be a measure space, as well as a collection of arrows that go between these objects. These arrows have a range, well, have a tail ahead of an arrow. So there's, we think of these arrows as, I guess, mapping one point in the space of objects to another point in the space of objects. We think of these arrows as mapping one point in the space of objects to another point in the space of objects. We endow these arrows with a partially defined multiplication and inverse operation. So the inverse operation essentially flips the direction of the arrow. There are identity arrows above every single point that act as the trivial transformation of that single point. Compose arrows. So if an arrow has the same tail, has the same range as the source of another arrow, or the tail and the head of an arrow match up, we can compose them to get a new arrow. If I could draw, maybe I could draw a little picture, but I can't seem to figure that out right now. So we'll just keep going. In particular, I guess I'll give an example of a groupoid before I start talking about these more particular instances. If you have a space of objects that exists of only one point, then all of the arrows are above that one point, and your partially defined multiplication is actually an everywhere defined multiplication operation. And this collection of arrows above that one point actually forms a group. So in the instance where our space of objects is just one point, then this is a group. Otherwise, this only has a partially defined multiplication operation. All right, we're going to impose on this object some nice structures. Our groupoids are in general going to be infinite. In general, they're going to be measurable. And so the structure that we're endowing on it is the structure of a standard Borel space, or we're asking for it to be a standard Borel space, measured theoretically or topologically. We ask for every single map involved to be Borel. All of our source and range maps are countable to one as well, which is the discreteness condition. And the space of arrows and the space of objects are both standard Borel spaces. And there's one other thing that I'm going to add to this groupoid. All right, so this definition might seem like a lot, but really all we're adding on is a measure on top of this topological structure that we have from this Borel groupoid. So we have a measure on the space of objects, which I refer to as G0. So our space of objects is a measure space, standard probability space, generally speaking. And having a measure on this space of objects allows you to put a measure on the groupoid by looking at the counting measure along every single fiber and crossing it, well, every single fiber relative to one of the fibering maps, and crossing it with the measure mu0 on the measure space. But there are two fiberings that we have going on. So there's a range map and a source map. So we can either look at all of the arrows that have range a given point, look at the counting measure on that, crossed with the measure along the base space, or the other way around, look at all of the arrows that have source at a given point, the counting measure along that fiber crossed with the measure mu0 in that direction. These a priori are different measures. And the condition that we ask is that these two, right, so you can always define these measures as long as you have this Borel probability measure on the measure space, but we ask for these two measures to actually be equal. And this is a PMP-ness condition. It's going to show up quite often, or rather this measure mu1, that is this counting measure crossed with the measure along the base space, is a measure on the groupoid, and it's going to show up quite often throughout the talk. So I just want to emphasize the fact that mu1 is a measure on the groupoid, and it's actually going to be kind of a very natural measure. In particular, the two ways that you can define it actually correspond. All right. It might be a little bit clearer why it's called PMP once you see the examples on the left slide. So let me go through the examples, and then hopefully the setting of groupoids will make sense. So the first example is this example of a group that I gave when describing groupoids. If you just have a single object, then your partially defined multiplication operation is defined, well, for every single pair of arrows that you're multiplying together, and this is in fact a group. You can also have any equivalence relation. So if you're familiar with the equivalence relation category, every single equivalence relation is a discrete PMP groupoid, just because, well, the PMP-ness comes from the PMP-ness of the equivalence relation, while the groupoid operation is now just the composition operation. Well, it's essentially, we think of our equivalence relations as sets of pairs of this base space, and we can compose elements if the projection onto the second coordinate of one corresponds with the projection onto the first coordinate of the other. So this way we're endowing it with an algebraic structure, although this algebraic structure, I mean, you can always endow it as long as we're looking at something transitive. The inverse operation is just xy inverse is yx inverse. So it's nothing too complicated. And then the setting that I most end up thinking about, or it's not exactly the most general setting, but it is a quite general setting. If you have a PMP action of a countable group, you can then define an action groupoid, which is going to encode entirely the action of this entire PMP action. So note that this PMP action doesn't necessarily need to be free. In the case where this is free, then this groupoid is the same thing as the as the orbit equivalence relation of the action as a groupoid with the groupoid operation. So they're isomorphic in the case where the action is free. When the action is not free, we're encoding the stabilizers and other things. So the groupoid operation is exactly encoding the action, right? So we think of a pair hx as the arrow that takes a point from x to h dot x. And then we can compose this with an arrow that takes h dot x to the point g dot h dot x. Right. All right, so any questions about these examples or groupoids? All right, so let me define now cost. So first off, cost is only going to be defined for equivalence relations in particular. And in the situation when your groupoid has no stabilizers, has no, well, essentially no arrows above a single point that send a point to itself. So if as I write right there, if the map that sends an arrow to its range and source pair is actually an injective map, then we call such a groupoid principal. And in fact, principal groupoids match up exactly with equivalence relations, and oftentimes I'm going to conflate the two terms. Equivalence relations just don't have the multiplication operation, but I mean, we can define that without any problem. So these are in bijective correspondence. So I'm only going to be talking about these principal groupoids or equivalence relations. And I'm going to define cost in analogy to the rank of a group. So I first define what it means to generate a groupoid. So this is exactly what you would hope it would mean. We have a notion of multiplication. A subset generates the groupoid if by multiplying n copies of that subset together, you and off to infinity, arbitrarily large finite numbers of copies of that subset together, then you get a conal subset. You get almost everything inside G. Right. And now cost is just defined as the size of the smallest generating set. So in analogy with rank, it's in perfect analogy with rank. And the notion of size that we use is this mu1 measure that I defined on the first slide, this natural measure on the groupoid. It really holds an analogy, well, and in particular, it really holds an analogy with the group setting. If you look at this definition, when instead of considering a principal groupoid, instead of considering an equivalence relation, you consider a group, then this is just the definition of the rank of a group. It actually does correspond. All right. I guess I should mention for people who know cost already, this is equivalent to other definitions via graphings and other things like this. It's pretty easy to see, in fact. It's a direct translation of the two notions. All right, so let me give a couple of examples. The examples I'm giving are actually going to be of cost of a group. So cost of a group is a slightly different invariant. We can define cost of a group by looking at the costs of all of the action groupoids of free PMP actions and looking at the smallest cost, well, the infimum of these costs. In fact, for most of the examples I'm going to give, the infimum is not necessary. It in fact matches up exactly. So you can think of cost as just the cost of any one of these free PMP actions. But I'll point out the case where it's unknown. So first off, for finite groups, it's a really elementary calculation to just, for finite groups, if you look at a free PMP action, every single equivalence class has sized that finite group. And so you can just come up with a generating set by hand that has cost 1 minus 1 for size of count. I guess it's important to say that for infinite groups, cost cannot be less than 1. Finite groups are the only groups that can have cost less than 1. So as soon as we get to infinite groups, so the first category of infinite groups is infinite amenable groups. And it's a bit of an overkill to cite Ornstein and Weiss for this, but well, it turns out that cost is in fact an invariant of orbit equivalence. And Ornstein and Weiss studied infinite amenable groups, or up to orbit equivalence very, very, very closely. And so it's a consequence of a much, much stronger theorem categorizing all actions of infinite amenable groups to be orbit equivalent, or free PMP actions of infinite amenable groups to be orbit equivalent. Right. More recently, and actually studying cost as opposed to orbit equivalence, Gaboriau, well, kind of published the first main results in cost by showing that free groups with n generators actually have cost n. He proved very nice theorems about treeability. The techniques that he used were rather combinatorial in nature in studying, well, what he called L graphings closely and cutting and pasting them and manipulating them fairly locally. More recently, Robin Tucker-Drob showed that inner amenable groups have cost 1, and he did this by studying the algebraic properties of these groups. So cost turns out to be monotone under various weak notions of normality, and he was able to find weakly normal subgroups of inner amenable groups that had very, very small cost.
Sorry, for infinite free group, cost is equal to infinity.
That's right. That's correct. For F infinity, the cost is infinity. So cost can take infinite values as well. Is that it?
Okay.
Yep. All right. And so for all of these examples, in fact, they were able to show that every single one of the actions of these groups has the same cost, has cost 1, has cost n. But more recently, Tom Hutchcroft and Gabor Pete showed that Kazhdan groups have cost 1, but the way that they did this was by finding actions, particular actions of Kazhdan groups that have arbitrarily small cost, or rather finding a particular action of Kazhdan groups that has cost 1, but they weren't able to show that every single action of a Kazhdan group has cost 1. All right. So essentially, these several examples kind of show all of the different known ways and techniques of calculating cost. So either finding it as an orbit equivalence invariant, or studying it measure theoretic combinatorially, or studying the algebraic properties, or so yeah, I didn't mention this yet, but yeah, Tom Cockcroft and Gaboriau used percolation theoretic techniques in order to come up with this action of Kaufman groups that at cost 1. So these are essentially the only known ways of calculating cost. I have one more example that I want to give in the equivalence relation setting, as opposed to cost of groups. But in order to define it, I have to define the full group of groupoid first. So, right, the notion of a section, partial section, and partial section, I hope are familiar to most of the audience. It's just a map that forms a partial inverse, or forms an inverse to the projection map that fibers, well, to the fibering projection map. In our case, we have two different fiberings relative to the range map and relative to the source map. So we can ask for a section to be a section for both maps, in which case we call this a bisection. And we define the full group as the group of all bisections. It's the collection of all bisections. It's a group under composition, taking inverses, and so on. It does correspond to the full group in the equivalence relation setting when your groupoid is an equivalence relation. But this full group, we're treating it as a subset of the groupoid, as opposed to treating it as automorphisms of the space. So from every single bisection, you can actually get an automorphism of the space just by the fact, well, okay, you look at a single x value, you look at S inverse of that x value. So you look at, S inverse of that x value is a fiber, but your bisection only hits that fiber in exactly one point. So by looking at S inverse, we get up to a point in the inside the bisection. And then that bisection, by looking at the range of that bisection, sends us to a unique image point of that initial point x. So we get an automorphism of the space, an automorphism of the measure space for every single element of the bisection. We might get the same automorphism for multiple bisections. So this is the only difference. We're recording which groupoid elements are encoding this automorphism, by which group elements we're actually moving. All right. There's an analogously defined pseudo group where we only consider partial bisections and therefore partial maps of the space to itself. All right. So once we have this full group defined, in some sense, it's an automorphism group of the equivalence relation. We can now state this theorem of Kekris. So Alekos-Kekris proved that if you have a PMP equivalence relation, and this equivalence relation admits a non-trivial asymptotically central sequence of elements, it's a long set of words, in the full group, then in fact, the cost of that equivalence relation is 1. So now I'm going to treat these, the sequence of these elements of the full group as automorphisms of the space, and asymptotically central just means that asymptotically it commutes with any single element of the full group in measure. And non-trivial just means that this commutativity isn't happening for a trivial reason. It's not happening because our sequence is tending towards the identity element. And this is going to be a common theme when I talk about intermediability shortly. We're going to have a commutativity condition and then a non-triviality condition as well. So, right. And this will be an important example to recall later on. All right, so I guess that's the last. I'm going to talk about cost for a while. If there are any questions right now, I'll take any.
So this condition is not more general than hyperfiniteness. Is it true that hyperfinite equivalence relation satisfy to this condition?
Yes, hyperfinite equivalence relations satisfy this condition. There exist equivalence relations that are not hyperfinite that satisfy this condition as well. Yeah, I guess it's possible to come up with particular examples, but this condition, I guess, originally was stated as, I think it's something about the outer automorphism, maybe the full group being closed inside the outer automorphism group, or something along these lines. It was originally stated in terms of the outer automorphism group and how it lives inside of the equivalence relation, and how it lives inside the entire automorphism group of the equivalence relation.
Okay.
All right.
So maybe if you have, if your equivalence relation is the orbit equivalence relation of like G times Z, for example. So you have this group, which is, you know, you can say you have a group and it has a non-trivial center or an infinite center. And if it has, if it acts on some standard probability space and you look at the orbit equivalence relation, then it should be, my guess, I think, I haven't thought about it, but right, does there exist then an asymptotically central sequence of elements?
It's not every single, so it's not that every single equivalence, every single action of these things will give such a thing, but yes, there will be actions of you can come up with groups that are G cross Z that will have actions that satisfy this property. Okay. You'll have to look at, I think, compact actions of these groups, so you can come up with particular examples.
Is it true that for any infinite group, the cost is natural number?
No, there exist examples of groups that admit a cost of any number that is greater than 1. So if you're given any positive, well, any number greater than 1, you can construct a group that has that cost.
So for each positive number, exists some group for which costs equal to this number.
Essentially, there's, I mean, yeah, it's a little bit different for numbers less than 1 because you only get these 1 minus 1 over n's that come from finite groups. But otherwise, yes. Generally speaking, or at least as far as the literature knows at this point in time, for irrational values, the only known groups that have irrational values of cost are infinitely presented, but otherwise, yeah, it's unknown whether you can have finally presented such groups, but you can definitely come up with infinite groups that satisfy, that have a given cost. Cool. All right, then let's proceed. So I'm going to talk about inner amenability now. So inner amenability was originally introduced by Epros, well, when studying or in relation to property gamma and von Neumann algebras. Property gamma is not going to show up in the talk, so I'm only going to talk about it in this context of groups. A group is called inner amenable if it admits a sequence of unit vectors, non-negative unit vectors in L1 of the group that are both conjugation invariant and diffuse. So conjugation invariant, well, this is a fairly natural condition to ask. Diffuseness is just asking for us to have conjugation invariance for a non-trivial reason, right? So again, if we let our FNs concentrate on the identity element of the group, then of course they're conjugation invariant in that case, but every group will satisfy this property in that setting. So examples of inner amenable groups, there exist plenty of examples, but the primary ones are examples coming from amenability. So if you have an infinite amenable group, then in fact, you don't just have a sequence of unit vectors that's conjugation invariant, you can actually come up with a sequence of unit vectors that's bi-invariant, that's invariant under the action on the left or the action on the right. course, this will be diffuse in that case. Groups with infinite center. If you have infinite center, what you can do is look at the center. You can put an ultra filter on the center and then come up with a sequence of unit vectors that approximates the mean that comes about from looking at that ultra filter on the center. Infinite direct sums, right? So if you have an infinite direct sum, you can concentrate, you can look at unit vectors that concentrate on the identity in the first n coordinates and then off of the identity elsewhere. So, right, you have 3 classes of groups. All of these, for all of these classes, intermediability comes about from the amenability of some subgroup or from some commutativity inside the group. But there also exist many finitely generated simple non-amenable such examples, in which case you don't have this intermediability coming either from amenability of a subgroup or commutativity of some subgroup. Okay, so these are a nice large set of examples. And
you mean uncountably many means they are not isomorphic?
yes, there exist many non-isomorphic such examples. I guess maybe I can say a word or two about how these come about. Yeah, these come about from studying, well, the topological full groups of actions of various amenable groups. And I believe using entropy of those actions as a distinguishing value. So something along these lines distinguishes these groups of isomorphism as well. All right. Okay, so that's about it for interamenable groups. But I'm going to talk about interamenable equivalence relations. So recently, Yoshikata, Kida, and Robin Tucker-Drob defined the notion of interamenability, or defined an interamenability in the context of groupoids. Said equivalence relations, but we're actually going to do it in the context of groupoids. And the definition is very similar to the definition on the previous slide. We just ask for a sequence of non-negative unit vectors in L1 that are conjugation invariant and diffuse. Such a sequence as an interamenability sequence. We impose an ergodicity assumption just because without the ergodicity assumption, there are slightly more complicated properties that you also need to impose. But in this case of ergodicity, exactly these 2 properties are enough. So conjugation invariance, well, there's a natural notion of conjugation by elements of the full group. I'm not going to get too into the details. And diffuseness is exactly the same condition. We're using mu1 in replacement for the cardinality on the previous slide. Instead of asking for finite cardinality, now we're asking whenever mu1 of d is finite. Yeah, mu1 of d is finite. Right, examples of such things. So I don't want you to concentrate too much on the definition. I'm just going to give a couple of examples of such things. So if you have a countable interamenable group and you have an action of that group that has discrete spectrum, then the action groupoid is interamenable. Asking for discrete spectrum, well, isn't necessarily a necessary condition, but it's definitely something that's required, or you require some sort of condition on the action, because if you look at any non-amenable group, in particular, there are non-amenable interamenable groups, then the Bernoulli shift of that group has, isn't interamenable. The Bernoulli shift of that group does not give an action groupoid that's interamenable. So it's still an open question whether every interamenable group has some action that gives an interamenable action groupoid. Okay. That's all I wanted to say about that. But in particular, since we have this nice rich class of examples of interamenable groups from the previous slide, this gives a nice class, a large class of examples of interamenable groupoids. Interamenability also passes, I guess, maybe it's relevant to mention, interamenability passes to subgroupoids as well. So any subgroupoid of such a thing as well will be interamenable. And the other example that I'd like to give are equivalence relations that have this non-trivial asymptotically central sequence in the full group. So in this case, you can define an intermediability sequence just by looking at the graphs of these TNs and looking at the characteristic function of these graphs. Everything translates exactly as you would wish. And so these equivalence relations are in fact intermediable. There exists intermediable equivalence relations that don't satisfy this property. There are examples that are shown in Yoshikata, Kida, and Robin Tucker-Drob's paper. So they already came up with examples where this is not an equivalent condition, but it does give a nice rich class of examples as well. All right, so now I can finally get around to stating our theorem, or getting close to stating our theorem. Before I actually state it, if I want to state it properly, I need to define groupoid extensions. But I'll ask you not to pay too much attention unless you're familiar with the setting already to what I mean by measure-preserving groupoid homomorphisms. By groupoid extension, what I want you to think of is free PMP action of the groupoid. Because it turns out that the category of groupoid extensions is exactly the category of free PMP actions of these groupoids if you define free PMP actions of these groupoids in an appropriate manner. As an example, as a demonstrative example, if we have an action groupoid, then the map that goes from the action groupoid to the group that was acting is a groupoid extension. So like this action groupoid is the groupoid extension of the, or in my terminology, is the action groupoid of the, or is a groupoid extension of the group gamma. Okay, so I can state our theorem. If we have a principal groupoid extension, so principal is corresponding to freeness of the action of an ergodic intermediable groupoid, then the cost of this equivalence relation is 1. So if we just consider the trivial groupoid extension, so if we just look at an intermediable equivalence relation and look at the trivial groupoid extension, then this generalizes and gives an alternate proof of Kekris's result about these equivalence relations that have an asymptotically central, a non-trivial asymptotically central sequence in the full group. And in the case where the groupoid is in fact an intermediable group, then these principal groupoid extensions are just free PMP actions, and this generalizes the work of Tucker-Drob. Right. There are also plenty of examples that come up that aren't covered by these two theorems, but it gives a nice simultaneous generalization of both of them. Right. So any questions about the statement of the theorem? Because everything I'm going to say afterwards, after this now, is going to be a little bit about the proof and things that make up the proof.
So this theorem applies to the special case when this calligraphy G is a group?
Yes.
So does it prove then fixed price for interamenable groups?
So yeah, Robin Tucker-Drob already had shown. I stated.
Oh, okay. He had already shown that. Okay. I thought
he had already shown fixed price for groups. A lot of the techniques that we use are generalizations of the techniques used there to this setting.
Okay. Thanks.
Is it true for group? If you have infinite group inamenable, then cost equal to 1?
Yes. If you have an infinite, interamenable groups necessarily have to be infinite. So yeah, if you have an interamenable group, then the cost of that group is 1 as well. In the sense that if you look at the free PMP actions of that group, then they will have cost 1.
But it is not equivalent to the condition that the cost equal to 1.
No, there's plenty of examples of groups that are not interamenable that have cost 1. There are property T groups that are not interamenable, for example, and these have cost 1. Good. All right, so I'm only going, so I'm going to completely forget about these principal groupoid extensions when saying things about the theorem. Really, it's a relatively uninteresting part looking at the principal groupoid extensions as opposed to looking at the ergodic inner amenable groupoids. So I'm going to outline how this goes when we're just trying to calculate the cost of an ergodic inner amenable equivalence relation. Right. So if the equivalence relation is amenable or hyperfinite, then we're done just by the same sort of orbit equivalence invariance that was done by Ornstein-Weiss. Confeld and Weiss did the same thing in the equivalence relation setting. Right. So really, the interesting case is looking at non-amenable, inner amenable ergodic principal groupoids. Right. For such a groupoid, we can actually find a subgroupoid that has cost 1 plus epsilon, at most 1 plus epsilon, just by finding the maximal amenable subgroupoid. This has cost 1, just by the previous lines, by Confeld and Weiss. And by adding an epsilon portion of generators, we can actually, well, by adding on an epsilon proportion of generators, the cost only increases by epsilon, and we get something non-amenable, right? And so the goal would be to compare these two costs. In general, however, just being a subgroupoid or just being a subgroup isn't enough to give you any sort of relationship between the costs. You require some sort of normality between the two things, right? The notion of normality that we're going to use is Q-normality. Definition's on the screen, but primarily the important thing is that you can witness Q-normality by looking at conjugates of the subgroupoid bisections and asking whether that collection of conjugates for which the subgroupoid is mostly stable is large in the sense that it generates the entire groupoid. So the important thing is looking at conjugates of the subgroupoid and asking whether for a large collection of these elements of the, for a large collection of partial sections, whether the conjugate of the subgroupoid intersected with the subgroupoid is large, is aperiodic. It has infinite orbits, every single orbit infinite. These are all different ways to say it. Under this notion of, I guess I should mention this notion of Q-normality was, I guess, originally introduced by Popa in 2004 or 2006, sometime along those lines. And it was observed by several people, I think Furman originally, that if you have Q-normal equivalence relations, and equivalence relations that's Q-normal another equivalence relation, then in fact cost is monotone. Then cost can only decrease if you have a Q-normal subgroup of a given cost. All right, so now, we had this non-amenable, right? We had this non-amenable subgroupoid on the previous slide of cost 1 plus epsilon. And if we were able to show it's Q-normal in the large groupoid, then we'd be done. Unfortunately, it's not quite Q-normal, but the main theorem that we were able to show is that as soon as you have this non-amenable ergodic subgroupoid, you automatically get an intermediate groupoid that is, such that H is Q-normal in K and K is Q-normal in G. So you get a lot of information about this, about the structure of this groupoid, as soon as we have this non-amenable subgroupoid. All right. And right. And if you'll recall what we did on the previous slide, right? This is exactly enough in order to prove that interamenable equivalence relations have cost 1, because we found this non-amenable equivalence relation that it costs less than 1 plus epsilon. And by iterating the Q-normality, we get this bound, right? How much time do I have left? Okay, I have plenty of time. Good. All right. So I'm going to talk a little bit about how to prove this this theorem, which is the interesting, I think, where a lot of the interest in the argument lies. So having an intermutable groupoid and you have a non-amenable subgroupoid of that groupoid, how do you find this intermediate groupoid K? Right, so we have the theorem written down again. The first thing to notice is that as soon as you have in general, I guess you have an action of a groupoid on itself by conjugation. Okay, it's not really an action of the groupoid on itself. There's some technical issues, but philosophically, this is what you have going on. There's an action of a groupoid on itself by conjugation. In particular, if you have a subgroupoid, you can even have an action of a subgroupoid on the groupoid by conjugation. And by looking at this, these, if we look at a collection of sections that kind of decomposes G with respect to this action, we ask for this to be, I guess, something analogous to a transitive set, rather a transversal of the action of H on G. If you have such a collection of partial sections that decomposes G, so if you look at H dot sigma for element sigma inside this collection of partial sections, then these partition G, if we have such a collection of sections, now we just look at the maximal set on which this collection of sections, when conjugate, on which this groupoid intersected with the conjugate of that groupoid is non-amenable. Well, nowhere amenable, in fact. Recall that for Q normality, we just had to check that this H intersect H sigma has infinite orbits, is aperiodic, and nowhere amenable in particular implies that on A sigma, this is aperiodic. All right. And we can immediately just define the groupoid K as the subgroupoid H unioned with all of the parts of sigma that lived above A sigma. All right, so H is just going to be K is just going to be H as well as all of the places where, all of the sigmas, all the parts of the groupoid where conjugating by that part of the groupoid leaves our groupoid H nowhere amenable. It's an elementary calculation just by sitting down and writing, just writing down what the conjugates are to show that H is in fact H is Q normal in K. There's nothing in particular to it. The interesting part is in showing that K is in fact Q normal in G. And in order to do this, we actually look at another action of H on the group. So there are two different actions of H on the group that we have going on. There's an action by left translation, as well as an action by conjugation. Now, because of the non-amenability of the subgroupoid, this translation action, I haven't defined what it means for an action of a groupoid on a groupoid to be non-amenable or amenable, but bear with the philosophy of just understanding that there is tension between these two things. So the action by left translation is non-amenable just because the groupoid itself is non-amenable. Just like in the group setting, we define amenability of the groupoid by whether the left translation action of the groupoid on itself is non-amenable. And so that's where the non-amenability comes in. And the action by conjugation is amenable due to the intermediability of the groupoid. So in the group setting, the action by conjugation of a group on itself is amenable if the group is interamenable. We want to show that K is Q normal in G. So in the group setting, there's a lemma that exactly relates how amenable actions and non-amenable actions interact together, just encodes this tension. So if you have a group acting on two different spaces, X and Y, and one of the actions is amenable, and then you look at the stabilizers of that action, then those stabilizers, and if those stabilizers act amenably on the other space with the restricted action, then the original action of gamma on Y had to be amenable. In particular, if you know that one of the actions is amenable and the other action is non-amenable, then you know something about how the stabilizers act. You know that the actions of the stabilizers are also non-amenable for some collection of x's. The stabilizers of some positive measure collection of x's is going to act non-amenably. So we translate this lemma and prove a surprisingly similar lemma in the groupoid setting that encodes a lot of the same exact information. And using this lemma, I'm not going to get into details of how we do this, but you can actually show that this groupoid K that I defined on the previous slide actually has full density inside the groupoid G. The notion of density that I'm using is with respect to, there's an inner amenability sequence on G, so we have a notion of density with respect to it. These inner amenability sequences are conjugation invariant and diffuse. And these two conditions are exactly enough to check the Q normality from the previous slide. The conjugation invariant tells us that when we conjugate K, to look at K intersect K conjugated by sigma, this is still going to have full density. And the diffuseness tells us that actually every single orbit is going to be aperiodic, that every single orbit is going to be infinite. All right. So I think that's all I have to say. Let me just double check. Yep, that's it. So I'd like to thank everybody for listening. Thank you very much for listening to the talk.
Okay, yeah, thanks for the talk. There are questions.
Can you give the simplest example of non-amenable or even non-inner-amenable group which has cost equal to 1?
Right. I think SL3Z.
Concrete group.
Yeah, SL3Z, I think.
Sorry?
Should satisfy this.
I don't understand. What group?
The SL3Z. So the special linear group. So the group of the special linear group of 3x3 matrices with entries in Z, I believe is both property T and non-intermediable.
For example, say SLNZ.
Yes. So SLNZ. Yes.
So SLNZ has cost 1 and non-inner-amenable.
I believe so.
Okay. Well, I have some interest in this topic, and I have some maybe more closer to ergodic theory point of view. I want to say that you didn't use in your construction of groupoid, you didn't use general co-cycle. You consider only counting measure. But in general, we can consider not counting, but some sigma finite measure. And this is important for some examples.
Yeah, maybe so on the groupoid. Yeah, we specifically consider this measure just because this is what we require for PMP-ness. But yeah, I'm certain that there are plenty of instances where a different measure might be appropriate.
And what's your opinion? Is it possible to give general universal model for action of group with cost 1 equal to 1? for example, it maybe it's more clear if I can say the following. If you consider hyperfinite group,